Welcome, students. In our last lesson, we talked about the connection between energy, work, and power. In today's lesson, we're just going to talk about what energy is, what are the different types of energy, how is energy transformed from one form to the other, and what is the law governing that, the law of conservation of energy, which is a powerful law in physics and governs most scenario situations that we're used to seeing in our lives. So the first question is, what is energy? Well, all the changes around you every day involve the conversion of energy from one form to another. It's what I suppose dominates our day-to-day life in terms of playing video games, keeping our food cool in fridges, and stuff like that we depend on day to day. That all comes about by the fact that we can convert one form of energy to another. So just like below on the explosion on the left, a bomb is going off in a building. Could we describe the changes that are occurring? Well, it's a movement of energy, a conversion of energy from one form to another. So let's just talk about some different types of energy. And we've already talked in a previous lesson that energy is the ability to do work, capacity to do work. So how many different types of energy can you think of? So we've already talked about the fact that potential and kinetic are sort of two ways to classify energy. And we talked about two different types of potential energy. Many different types of potential energy. One of them that we talked about is lifting a ball up to a height. The ball is traveling up the hill and it would get gravitational potential energy. So that is the potential for that ball to do work and assisted by gravity in that case. We also talked about, in class, we talked about spring potential energy. If we compress down the spring, then there is an elastic potential energy, the potential for that to spring back and that energy to convert into kinetic energy. Another type of potential energy we talked about is chemical potential energy. So the potential energy stored in a chemical bond that allows energy to form on release of that energy bond. Think of things like nuclear fission, which is the splitting up of bonds on a nuclear level. So you could actually make a case for moving that into the potential and kinetic, because it has bonds have they have potential, but all of these could and have the potential to be transferred into another energy form. And we talked about the fact that when we talk about kinetic energy, we're really talking about the motion of objects. So if you'll excuse the Fred Flintstone's interpretation of a car here, this car, when traveling, has kinetic energy, has the energy of motion. And so we are already familiar with many of these types of different types of energy. So could you name at least one form of energy associated with each object in bold? A bonfire roasts a marshmallow. Well, I'm going to put one form in, and you guys can think of many more. Heat is actually a form of energy, the movement of molecules. A rugby ball smashes through a window. Maybe we might put that down as kinetic. I would challenge you guys to think of other forms of energy, not just kinetic. There's other energy in play there when that is happening. So think about things that other different types of energy. So the two main types of energy we learn about firstly are kinetic and potential, specifically gravitational potential. And we already discussed this. Kinetic energy is the energy of motion. It's defined by a very simple equation, half mv squared. So when you don't have velocity, you don't have kinetic energy. Likewise, potential energy is defined by the equation mgh, where m is mass, g is acceleration due to gravity, and h is the height from a reference point. And so right here, if the reference point is the ground is in green, then Wile E. Coyote, while breaking the laws of physics, has the potential to fall through that height, delta H. And so there's a potential there. His mass, if known, you could multiply by gravity and delta H from the ground as a reference point. And we could calculate the potential energy. That's the ability for him to do work. So one of the fundamental laws of thermodynamics and physics is the law of conservation of energy. It applies on many different scales, big and small. It states that the total energy of a closed system always remains the same. That is, the initial total energy, ETI, is equal to the final total energy, ETF. Now, this concept of a closed system is very, very important. And that is a system where matter and energy are kept constant. So matter and energy are constant. We know that not to be true in many situations in our everyday life, but if we can look at closed systems and if we can assume that those things are kept constant, then we can assume that the energy, total energy, is just merely transformed from one form to the other. The wolf presents a situation, a day-to-day situation, where the mechanical and the total energy is not actually kept constant because it's not a closed system. A closed system would not allow energy and matter to escape. There is an escaping of energy in the form of external, what are sometimes viewed as external energy. So while the wolf is walking, there is, some energy loss in terms of heat and sound. They're generally accepted as external energies. So for physics at this level, we say that would not be a closed system. So what would be an example of a closed system? Well, a good example of a closed system would be maybe a roller coaster. Okay, so a roller coaster, you got the roller coaster set up, and we're assuming that there's no loss of energy through heat and sound. And we have to work on assumptions here, like in many of the fundamental basic physics. And we have a carriage here. And so what we're saying is that the energy, total energy of the carriage as it moves through the roller coaster, the energy at the top at the section number 1 is equal to the energy at section number 2, which is equal to the energy at section number 3. If we ignore energy lost to its surroundings, if we can treat it like a closed system. So energy loss would be in the form of heat or sound. So an example of the girl on the swing, there is a transfer of energy from one form to another, potential energy, right across to kinetic energy as the swing is in motion. At the very first point where the swing is pulled back, it's all potential, and the swing has the potential to move through a gap of delta H. So remember, that would be mg delta H, and all that's transferred to kinetic energy. Likewise, with a batter hitting a bat, we have potential energy in the bat at the very beginning, and all of that potential energy can be transferred to kinetic energy. We would also have heat between the bat and the ball. We would hear the ball, so there would be sound energy. So the reality is there's lots of energy transfers, or sometimes called transformations. And we can go through some other examples, which we will go through in class. So what do we call this total energy? Well, it's called mechanical energy. Mechanical energy is generally accepted as the energy possessed by an object due to its motion or position. So back to those two forms of energy, simple forms, kinetic and potential. And it's often written as EP, E potential, plus EK, E kinetic, when we are dealing with an isolated system. That's very, very important. So to be an isolated system, we must have no outside forces, no friction. We're ignoring friction, we're ignoring heat, sound, those type of things to make our life easy. So total energy would be a half mv squared plus mgh. Okay, so let's look at that in principle. So these three scenarios where we have athletes, we're going to try to think about, are they in motion? Is it all potential energy, all kinetic, or a combination of both? Well, in instance number 1, the athlete on the top left, the athlete right at that motion where they're not moving up or down, there's no kinetic energy, it can be seen as all potential. In the instance on the right, the athlete is moving, and we have a combination of both. Right at the bottom, where the pole vaulter is running before they've left the ground, There is no delta H between them and the ground. They don't have any height, so therefore gravity does not have the ability to do work. It's all kinetic energy. So it brings us to a couple of examples, some problems. So some practice problems. If the cliff is 30 meters above the ground, how much potential energy does the ball have on top of the cliff if it weighs 4 kilograms? The way to set these up is to always ask yourself what has been asked for. So what we're being asked for is the potential energy the ball has. So generally we would write out EK plus EP, and we would say, do we have to set up, do we have kinetic energy at 30 meters? Okay, H is equal to 30 meters. Is there any kinetic energy when the ball is on the cliff? No, there's not, so we don't need to worry about that. And sometimes you might find it useful to draw a little bar graph. There's zero kinetic energy, but there is some potential. That potential energy is in the form of mgh. So EP is equal to mgh, and then we can substitute in some values. 4 kg. G is going to be 9.81 if we use the accepted standard for Earth, and then that's multiplied by 30 meters. And that should give us an answer which is 1,177.2 joules. Remembering that energy and work is generally written, the unit is joules, so it's 1,177 joules. So the question is, knowing that energy is not created or destroyed, what will be the ball's kinetic energy the very instant before it hits the ground? So as the ball moves down, the ball is going to move from here. Ball is going to fall from a height which it had potential energy. All of that is going to be transferred until just before the ground. Obviously, when it hits the ground, that's an external force that acts on the ball. By the way, we do not treat gravity as an external force. So what is the kinetic energy before it hits the ground? Well, we know that mechanical energy at the beginning is equal to mechanical energy at the end. And we sometimes write the mechanical energy at the end as ME prime. This little line is known as prime, and it's after the fact. So you can say MEI equal to MEF if it's easier. Up here we had no kinetic, it was all potential. Right at the bottom we had no potential because the H is going to be 0. Right from this reference point right before the bottom, H is 0. So it's changed to all kinetic. Okay, so what we have at the very beginning, we had mgh. At the very end, we have all kinetic, which is a half mv squared. Just using basic mathematics, the m's can cancel. And so what we're left for, if we want to find the kinetic energy at the very instant before it hits the ground, actually, there's a couple of things that we can solve here. The very instant before it hits the ground, the kinetic energy is going to be the same. So it's going to be the exact same figure, 1177. So what you started with is what you finish with. However, we can also calculate something else. So the mgh is equal to a half mv squared. And so you will get the same value for that. But what will be the ball's velocity before it touches the ground? Okay, so we've set it up and we said mgh is equal to a half mv squared. And we cancel these g's, these m's, sorry. And we wanted to find the velocity. Well, we can simply isolate for velocity is equal to v squared. And so v is equal to 2gh, the square root of that. Right? So we can get, if we have the height beforehand, we have g, we can get what the velocity is going to become. And actually the velocity of a ball just before it hits the ground, which is dependent on height and not on mass, is 24.3 meters per second. Okay, so I'm going to give you guys a practice problem for tomorrow. Wile E. Coyote is trying to drop a boulder off a cliff. He wants to know the speed of the boulder at various points. He supplies you with the blueprint shown here. The coyote wants you to determine the velocity of the boulder at several heights above the ground, assuming no air resistance. Now, what I want you guys to bear in mind if the boulder is at 30 meters, so the boulder is at 30 meters above the ground, does it have potential energy? Yes, it does. It's 30 meters higher than the reference point of 0. Does it have kinetic energy? Yes, it does, because it's moving. And so you're going to have to isolate for kinetic energy from the original potential. So using part B as an example, ME is equal to ME prime. At the very beginning, what is causing the energy of the boulder? Well, there is only gravitational potential. At ME prime, which is to say 30 meters, there is, we'll call it height 2. There is mgh2 plus the boulder is moving, so there's a half mv squared. So now, of course, again, we can cancel these m's. And we can start putting in some values. Actually, so let's leave the value of g, which is 9.81. The height at reference point 1 is 45 meters. Okay, so it's 45 meters. The height at reference point 2 is 30 meters. And we've got v squared. Okay, and now it's just a question of putting in your value for g here, figuring out these values, and then isolating for v. And know that you can do that anywhere along the way, assuming that this is an isolated system, and remembering that it's just energy just transferred from one form to another, and that you can calculate the velocity at various points. We will continue this lesson in class tomorrow.